These are the examples that go with lesson 4.7, inverse trigonometric functions. This is part 2. Example 6. Find the exact value of sine of inverse tangent of 12 over 5. 12 over 5 is not one of the coordinates that's out there on the unit circle, so sometimes it helps to draw the triangle so you can get a picture of what's going on. And then we can use the SOHCAHTOA to figure out what the trig function is that we're looking for. Okay, the inverse tangent, first of all, since this is positive, it's going to return a value that's going to be in quadrant 1, and that's because the inverse tangent is defined to be positive in quadrants 1 and 3, but the domain is quadrants 1 and 4. So this is going to have to be the quadrant 1 angle because the tangent here is in fact positive. All right, so that helps when I'm going to draw the picture of it. So here we go. We know our triangle is going to be over here in quadrant 1. We'll drop our altitude down here. The angle is going to be down here. The angle actually isn't going to matter a whole lot. Okay, the inverse tangent, remember, is going to be, or the tangent actually, I'm sorry, is going to be y divided by x. So that means our y value here is going to be 12, and our x value right here is going to be 5. And we do not have the hypotenuse over here. So let's use the Pythagorean theorem to see if we can figure out what the hypotenuse is. All right, that's going to give us a squared plus b squared equal to c squared. This is 25 plus 169 equal to r squared. This is going to give me, that was 144. I'm sorry, I'm getting ahead of myself. Let's try that again. 12 squared is 144. And then when we add 25 to 144, we get 169. So we'll square root both sides. And then the radical and the square will cancel, and I know that r is going to be equal to 13. The sine is defined to be the opposite side over the hypotenuse, or we could say the y coordinate over the r coordinate. And in this case, we knew y was 12, and we just found r to be 13. And so this problem will simplify into 12 over 13. Example 7, find the exact value of cosine of inverse sine of negative 2 over 11. We're going to work this the same way we did example 6. The inverse sine, you'll notice, is negative this time, and the inverse sine is negative in quadrants 3 and 4, but the domain for the inverse sine is quadrants 1 and 4. That means that we're going to have to draw this triangle in quadrant 2 because, I'm sorry, in quadrant 4 because the sine is negative in quadrant 4. All right, so let's look at the picture. Here's our triangle. Drop in the altitude. The sine is defined to be the opposite side over the hypotenuse, or y divided by h, or y divided by r. That means if our angle is located right here, this side is going to measure 2, and I'm actually going to put the negative 2 here because we're down in quadrant 4 and y's are negative. And then the radius over here is going to be 11. Because we knew that this part right here was y divided by r. Now the cosine, this part right here, is x divided by r. That means we at least know this is going to be divided by 11, because we already knew what the r value was. But we don't have this one right here. So let's use the Pythagorean theorem, and we'll do a squared plus b squared equals c squared. We got a squared plus 4 equal to 121. And then x squared is going to be equal to 117, and that's going to be after we subtract 4 from both sides. And we're going to square root both sides. And I know that the square and the square root are going to cancel. And let's see, 117. I know 3 can go in there. 3 can go into 11. 3 times 39. This is prime. And then 3 can go into 39 13 times. Now this is prime. That means my radical can break down into 3 times the square root of 13. The 3 out here came from the fact that I had a pair of 3's right here. Alright, so now I can say that the cosine is my x-coordinate, which is 3 times the square root of 13, divided by the r, the radius, which is 11. And so this problem simplifies to 3 square root 13 over 11. Example 8. Write the expression tangent of inverse sine of x divided by x squared plus 9 as an algebraic expression for x is greater than 0. Well, again, we're going to have to draw the picture of this thing, and I'm going to put this in quadrant 1 because they told me that x is a positive number right here, which means that this is going to be a positive right here. And remember, the inverse sine is going to be positive in quadrants 1 and 2, but the domain for the inverse sine is quadrants 1 and 4, and the inverse sine is positive in quadrant 1. So let's draw our triangle. We know we're in quadrant 1. Drop our altitude. Our angle is going to be located right here. The sine defined to be the y divided by the r. So this is going to be a little confusing because y is equal to x here, but just stay with me. The radius is going to be the square root of x squared plus 9. And we are looking for the tangent, which is y divided by x. So we will find that out in just a second. We need to figure out what this side is down here, and since I've already used up x, I'm just going to give it another name, and I'm going to call it a, because I'm going to have to use the Pythagorean theorem to figure out what's going on here anyway. Alright, so let's do a squared plus b squared equals c squared. That gives us a squared plus x squared. Over here, the radical and the 2 will cancel, so we've got x squared plus 9. Now when I solve this equation, I'm solving for a, so when I subtract this x squared over here, they're going to end up canceling each other out, and we're going to be left with a squared equal to 9. Let's square root both sides. The radical and the square will cancel. We have a equal to 3, and I'm going to leave this a positive 3 because remember we're over here in quadrant 1. Alright, this expression is going to simplify into our y-coordinate, which was x, divided by the x-coordinate, which we just found to be 3. So our expression will simplify into x divided by 3. Example 9. For the construction of a base of a house, a 16-foot by 6-foot wooden frame is made. Find the angle that the diagonal beam makes with the base of the frame and round to the nearest tenth of a degree. Let's look at a picture of what's going on here. The base is going to be a rectangle, and the sides are going to measure 16 feet and 6 feet. And then the diagonal beam, that should go from one corner to the other one. Now, rectangles have 4 right angles in there, so we can just put one in right there. And we want to figure out the angle that goes from the diagonal beam to the base. So essentially we're looking for this angle right here, the diagonal beam and the base. And I'm just going to call that theta. Okay. In this problem, here's the right angle. That means our diagonal beam right here is going to be the hypotenuse. This side over here, this is the opposite side. That makes this one right here the adjacent side. Okay, now we're going to use SOHCAHTOA here. And I don't know the hypotenuse, so I won't be using sine because it needs a hypotenuse. I won't be using cosine because it needs a hypotenuse. That means I have to solve this problem with tangent. Therefore, the tangent of the angle I'm looking for is equal to the opposite side divided by the adjacent side. Now we don't know the angle, okay? So if the tangent of the angle is 6/16, we can say that our angle is going to be equal to the inverse tangent of 6/16. And then we can put this in our calculator. Be sure you're in degrees, because if you're not, you're going to get the wrong answer here. We're going to do second, and then tangent, and then 6/16. And that's going to return a value of 20.6 degrees when we round it to 1 decimal place. Example 10, approximate each expression in radians rounded to 4 decimal places. Part A, the inverse secant of -1. Okay, the first thing you're going to notice is that there is not a secant key on your calculator, and that's a problem. But I do have a cosine key, and that helps because I know that the secant is the reciprocal function for the cosine. And what that means for me is that I can change this into an inverse cosine problem if I will do the reciprocal of this fraction. When we put this into the calculator, the inverse cosine of, I guess that should actually be -1 divided by 1. Sorry about that. Okay, so we've taken the fraction 1/-1, we've made its reciprocal into -1/1. That changes our secant function into a cosine function because they are reciprocals as well. Okay, so now we put this in the calculator. Make sure you're in radians. Okay, we got to change over from degrees to radians. And we're going to do secant cosine and then -1/1. And this is going to give me 3.1416. That should look familiar to you because this is actually pi, which is on the unit circle. So we knew that the angle where the cosine was -1 was going to be over here at pi, but it asked us to round to 4 decimal places, so this is the one that we want right here. Okay, part B, the inverse cotangent of -5/12. The reciprocal function for the cotangent is the tangent. That is on my calculator, but the cotangent key is not. So let's turn this into an inverse tangent problem. And since I've done the reciprocal of this trig function, we need to do the reciprocal of the fraction here and turn this into -12 over 5. And now it's ready to put in the calculator. We're in radians. We do second tangent, -12 over 5. And that returns a value of -1.1760. Now, this one we're not finished because the inverse tangent has a domain that's going to be in quadrants 1 and 4. But the inverse cotangent has a domain that's in quadrants 1 and 2. So this value that I got is actually an angle that's in quadrant 4. But I want the one that's going to be here in quadrant 2 because the problem asked me for the cotangent. It didn't ask me for the tangent. All right, let's take a look at the picture. -1.176. That's going to be down here. All right, -1.1760 has a reference angle of 1.1760. That means that in quadrant 2, the angle we're looking for goes from here to here. This reference angle is also going to be 1.1760. And if I want to know what this angle is right here, then I need to, let's see, from here all the way across is pi, but we need to back up 1.1760. That means the angle I'm looking for is going to be pi minus 1.1760. And since we're staying in decimals, you could leave it like that, but since the directions tell us to round it to 4 decimal places, we're going to subtract 3.1416 minus 1.1760, and that gives me the angle 1.9656. There's my solution right here, the angle that I'm looking for. Okay, so the tangent is really the only one that you need to look out for on a problem like this. If you're going from cotangent to tangent or tangent to cotangent, you're going to have to pay attention to your quadrants. And again, that's because their domains are different. The tangent's in 1 and 4, the cotangent's in 1 and 2. You don't have to deal with that with the secant and the cosine because they're positive and negative in the same place, so they have the same domain and range. I'm sorry, they have the same domain. And then the cosecant and the sine are the same. They have the same domain as well. They're both positive in quadrants 1 and 2, and so their domains are quadrants 1 and 4. So we had to figure out the answer using the tangent, because this is the key in the calculator. The answer it gave me was in quadrant 4, but the cotangent, this is not in the domain of the cotangent function. So I had to use my reference angles here to figure out what this angle was to get me over into quadrant 2.